Okay, the next talk in today's session is by Nima Rasekh, who is theoretically at EPFL. And he's going to tell us about elementary infinity topos theory, constructing coproducts in locally Cartesian closed infinity categories. Please go ahead.
All right. Before I start, thank the organizers for giving me the opportunity to speak here. And I want to thank you all for, coming and attending this talk. So when I was preparing the talk, I realized it's a little bit not enough time to give all the details. And it's a little bit too much time to give no details and just say the result. And so because this is kind of like a job event, I decided to spend a couple of minutes and do something unusual and talk about why I'm even here in the first place, and why I ended up in the hardest event, given that I'm not really a type theorist. So I'm going to do a 5-minute introduction to myself, I guess, for all the people who don't know me, which based on the list of participants, is actually quite a lot of people that I've never seen, I think. So what am I doing here? I'm really, by nature, a homotopy theorist. So the things I use are infinity categories mostly, and I also think about THH and vibrations of infinity categories and that kind of stuff. But one thing that I'm also super interested in is foundations of homotopy theory. I'm always kind of concerned that most of homotopical mathematics has been developed in kind of one single foundation. And the thing that I always have in mind, I'm not a foundation expert, but the thing I have in mind is a contrast to non-homotopical mathematics, where if non-homotopy theorists want to prove something, they have these options of they have these axiomatizations and they have models, and yeah, you can kind of choose what axiomatization you want, right? You can say, okay, I want the law of excluded middle, or I don't want it, or I need the axiom of choice to prove something, or sometimes you see analysts, they need the continuum hypothesis to prove something about real line and certain subsets. And in a lot of homotopy theory literature doesn't do that yet. They prove kind of cool results, and it's not always clear which foundation you really need. Do you need the law of excluded middle to prove it, or can you do it without? And yeah, so what I would like to see is a homotopy theory that makes clear kind of where the boundaries are. So that's the dream, right? So, and that's precisely what attracts me to HOT, right? So the HOT is kind of the way I see it. One aspect of HOT is precisely giving you these kind of results, right? So there's obviously the proof kind of checking aspects and lots of other stuff, but one kind of aspect of HOT is the so-called synthetic algebraic topology, is giving you kind of results that then you know, okay, what foundation do you need to really prove it. I think this first one is kind of really illustrative, right? So it's one of the first results that you see in HOT, that is in book HOT already, and it was known kind of. But it's kind of interesting. Even this result, if you just asked, I would say, an algebraic topologist who obviously knew pi1 of S1 as Z for decades, but if you ask them, okay, if you change the foundation of set theory, you remove the axiom of choice or something, or you change the set theory foundation somehow, is it still true that the fundamental group of the circle is just a free group? I don't think anybody could have given an obvious answer, even in 2008 or something. So having this kind of foundation, I think, is very useful. And so, as I'm still a homotopy theorist, I like to approach this from the infinity category perspective. And then so this kind of banner of approaching foundations using infinity categories, or semantics, is what's generally called as elementary infinity topos theory. And so one of my dreams is to know as much as possible about this. Whatever I can know about this, I want. And unfortunately, maybe, or fortunately, because there's opportunity, there's not as much stuff as there is in homotopy type theory. The literature is still much, much smaller, but it's still better than it used to be. So let's just take a time machine and go back to the year 2017. And so here we are in Snowbird in Utah, and there was this mathematical research community, MRC, and this is June 5th, 2017. And there was a gathering of a bunch of homotopy type theorists and homotopy theory enthusiasts like me. And we were discussing, okay, what kind of stuff you can prove about this elementary infinity topos, or some notion like that. And these are all kind of questions that we had no idea about at that time. We were discussing, okay, which one of these can we prove? And in the last 4.5 years, things have improved. We do now have some results. So for example, we now know that, okay, you can construct a natural number object using similar to Hart, where we get like truncations, and we have like non-presentable examples, which we didn't have at that point. And one of the projects that has come out of this, like the one project that actually started there, here is constructing coproducts, because right there in front of this board was, I was there and Jonas was there, and we started thinking about, okay, can you construct coproducts using kind of like some axioms or something? And this is one of the questions that has now been answered, and that's kind of what I want to focus the talk on for today. So this was the intro part, and now I want to get to the actual talk that was promised. That was the actual title. And this is all joint work with Jonas Frey, who I think was in the audience, or maybe not, but I think he was there. Yeah. So let's start with the real part. I will use the word infinity category a lot, depending on who you are. If you're comfortable with this, it's like kind of quasi-categories, but it doesn't really matter. We use kind of basic properties of quasi-category theory, and so any kind of equivalent infinity cosmos would work, common single spaces, one composition sets, whatnot. If you don't know what these things are, you should just imagine like a category, and you have mapping spaces, but the enrichment is kind of like weak, like you have like some weak notion of composition. And any kind of standard notion of a categorical property like adjunctions and limits and colimits and everything like that has some kind of infinity categorical analog. And that's all I'm going to say about this for the purpose of this talk. Okay. So what we want to study is that certain infinity categories have coproducts and colimits, right? So that's kind of the goal of this talk. And I guess one good question is, why would we expect this to be true? Where does the motivation come from? And the motivation comes from a word of like elementary topos theory. So here the topos is like one topos theory, like classical category theory. And in order to like state that result first, let me remind you / introduce to you the notion of a subobject classifier. And here I'm already in the setting of like infinity categories. So I want to say a subobject classifier is like a choice of object and a monomap such that like I have this natural bijection here of mapping spaces. And notice like, so you might say, okay, what does it mean inside infinity world? And there's like a nice elegant description of mono. So I can just say a map is mono here. If this is a pullback. So this is true in one category theory, but this is also true in infinity category theory. This actually doesn't change. So it's like a nice, easy description of a pullback. Now, so this, just not to be confused, this is I. There you go. And I want all monomorphisms over a certain object to be classified by maps into this subobject classifier, and then it'll be obtained by a pullback of this universal monomorphism. And so whenever I have a locally Gaussian closed category with finite colimits and subobject classifier, then I have an elementary topos. So that was like the original definition of elementary topos, going back to the work of Tierney in the 70s. But then very soon thereafter, people realized, okay, you don't really need the colimit part because you have this result, and with different proofs that states that if you have a one category and it's locally Gaussian closed and you have the subobject classifier, then you just get all finite colimits for free. So the assumption of finite colimits is redundant. And now, if you open, for example, the book by McLean and Murdyke, if you look at the definition, it doesn't have finite colimits anymore. It's proven later that you can deduce it. So that's kind of been standardized. And so if you just look at this result, the naive theorem that you could like kind of ask yourself, so the naive conjecture is the following. Namely, if you have a local Gaussian closed infinity category and you have a subobject classifier, then you have all finite colimits. So is this true or is it not true? If it is true, how true it is? We have counterexamples. What can we do with this? Right. So this is the goal of this talk. And before we kind of go into the proof, let us understand how the proofs of this kind of result went to kind of understand, okay, how can we generalize? So the proof by Pare is kind of like a so-called one package deal, in the sense that I recognize that the opposite category of an elementary topos is monadic over itself via this power object map, like the exponentiation with the subobject classifier. And because it's a category of algebras, it will preserve all the limits that exists in E. And so it has all finite limits. And because op has finite limits, E has finite colimits. So there you go. This is like a really elegant proof. And this is precisely the proof, for example, given in the textbook by Mikkelsen and Pare. But it's also precisely not useful at all if you want to generalize, because it's a one package deal. It kind of gives you the whole result together. And so if this condition doesn't hold, you kind of have nothing. And so just to give you like a concrete sense of how much it fails, not only is it like, even let's say you take E to be spaces, you think of spaces, then not only is this not monadic, it's not even conservative. Like this exponentiation with respect to like omega will not preserve like equal, like will not reflect equivalence. So you cannot use it at all. So let's go for the second proof. And the second proof is attributed to Mikkelsen. I'm kind of confused at where it came from, but it does exist. And here we do an ad hoc approach. Like, so remember like classical category theory, which states that if I want to have finite colimits, what do I need to do? I need to have an initial object, finite coproducts, and a coequalizer. If I have those three, then I can construct all finite colimits by doing together diagrams. And so this is kind of how the proof goes, right? So you first start by observing that these kind of like this subobject classifier, there's like this sub is always a Hating algebra structure. And so this you kind of a Hating algebra in particular involves like the minimal subobject. And so that minimal subobject will be the initial object. So you can prove this. And then because it's a Hating algebra, you have joins. So if I have two objects, I can recognize them as a subobject of some kind of larger object, and then take the join of them. And I can use a similar approach to construct coequalizers. And so this approach is like much better because it's broken down into steps. And so it's not true that this just generalizes. This is still false. However, because the proof itself kind of has several steps, what we can kind of do is look at the actual proofs, and whichever ones kind of hold more or less, just keep them. And whatever fails, you kind of adjust and you keep going. And you have like a complete proof or a counterexample, depending on what it is. So let us use this approach and try to prove something. So the first item goes through more or less the same way. Like you don't really need any change. And the key observation is that this thing sub is always a set, or like a zero type here, what I mean, right? Like it doesn't have any interesting homotopical structure, even if C is an infinity category. Like that has no influence on it whatsoever. It's always, because you're looking at subobjects, so there cannot be any interesting homotopy theory. So you more or less can use exactly the same argument as the one you would use in one category theory to deduce that if you have a subobject classifier, then the sub A has like a finite joins, and by finite also including empty, right? So it has a least subobject. So yeah, this one is more or less fine. You don't really need to do like a lot of new mathematics, fortunately. This doesn't generalize, so like the next step needs some work. Namely, now I want to construct initial object. And so I can like start with the same idea. I kind start, okay, say omega or like 1 or whatever. Like you take any object as a matter of fact, and then that has the least subobject. And so now I want to prove, so this least subobject is an initial object. And here I need to be able to say something about maps into I. And okay, like here's one of the things where I need to have some tool that allows me to simplify homotopical data into like subobjects. And the key idea is to use this functor is contra, which comes from kind of like the motivated by this construction of homotopy type theory, which takes a map and sort of give a concrete construction. If I have a map A sitting over X, what I can do is I can take like this diagonal and I can push it forward along like some kind of projection. And this is precisely is contra of A, which is like sitting over X like this. And like one of the things you can prove, so this is the push forward here. And one of the things you can prove is that this map is in fact mono, i.e. is contra of A is in fact a subobject of X. So this is really like a map into subobjects. And moreover, you have this cool fact that this map is terminal, it is an equivalence into X, if and only if you actually get the maximum subobject. So this kind of allows you to recognize non-trivial maps of any truncation level just by looking at maps that are subobjects. So it's like a very kind of powerful result in that sense. So this is it really goes back to like ideas from Hodge, kind of work by Woodwardski, and it's also in Burkhardt already. And there's already observed that this is a mere proposition, so to speak, like it's -1 truncated. I think it was at least the first place I saw it is there was work of Schumann, who adapts this to the model categorical setting in his work of like constructing models. And like we are using this kind of like an infinite categorical setting, like very analogous to the previous work. So now using this, so combining now the fact that here sub I is trivial and the fact that I have this is counter map, I can immediately deduce that this if I is this in like this least subobject, then all of C over I must be trivial. And now I want to use this to prove that I is initial. And that's not that hard anymore, because for any other object X to the I is like a push forward of the projection map, and the projection map is trivial. So the push forward is trivial. So the mapping space from I to X is a contractible space, which is like the definition of being initial. So you can construct an initial object here. And so the construction is not too hard, but in order to prove that it is initial, you do need this kind of additional kind of homotopy type theory perspective to reduce homotopical data to subobjects. All right, so now I have an initial object. The next natural thing is I want coproducts. And here, let me like review quickly the proof that I mentioned by Mikkelsen again. So here, how do I want to do this? I want to use these two facts. Namely, it's known that so A sits inside like its power object as like elements, and there's like a disjoint point which corresponds to like to the empty one. And so in particular, then for anything, I get like such a pullback diagram. And what I can do is I can take any other subobject and do the same trick. So I also have this pullback diagram, and now I just product those. And if I product them, I have now A and B sitting disjointly inside this thing. Now, why does it matter? Because now all I have to do is I can take the join using the fact that this is a hiding algebra. And now I prove that the join is in fact a coproduct. So notice there's really like two steps here. First is recognizing that I can put any two objects disjointly into something larger. And second, there's the step of like, if I have something, this thing constructed, can I prove it's a coproduct? And that second part is true, but it is actually in some sense like the least kind of trivial part of the work. To realize that whenever I have two objects in this local closed infinite category with the classifier, and I have any object C, so that I can embed A and B disjointly. So this needs to be disjoint here, to be clear. Then the join inside C is a coproduct. So this is a direct generalization of this result here. And to prove, I have time, perfect. So let me like explain to you how the proof goes more or less. And so first of all, I will make the simplification. So I will just assume that C is, as a matter of fact, the coproduct of A, the internal join of A and B. I can just reduce it to that subobject. I don't need anything bigger. And then I can also assume C is just one by working over it. And now what do I need to prove? I, by definition, need to prove that if I have any other object, then a map from one into it is equivalent to a map from A into it and a map from B into it. So this is like old school definition of the coproduct. And I can use the internal Cartesian closure to translate this into saying, okay, what I really want is that if I take this projection map and I take here a choice of elements, I want this to be contractible. Right, or like this is an equivalence, so to speak. That's like the goal. So how can I do that? And here again, like this is why this is contra is so useful. I have a map. A priori, P could have any truncation level. P could be like very complicated. But P is an equivalence if and only if is contra of P is trivial. So now I can just think of this. This is inside sub of 1, right? So here I have a map into 1. I take is contra of it, and now it's just a subobject of 1. Just like super nice, because subobjects are easier to work with. And now I know that A plus B is 1. So a 1 kind of breaks down nicely into A and B. So all I need to do then is to just check out the restriction to A and the restriction to B. And I need to know these are like precisely A and B. So if I can prove these two things, then I'm good. And they're symmetric. So as a matter of fact, I need to only prove one of them. Like, really no difference. So what I do is I say, okay, I want to pull back along A, this pullback diagram that's been given to me. And here's some like calculation that I'll skip that will tell me that if I, so here's my A star P by definition, this is just A. This is A star of X. And so now here's two assumptions that I will skip, namely A star of X to the A. This is just A star of X. And more importantly, A star of X to the B is trivial with object. So now here I precisely just get A star of X. This is like some kind of identity. So there you go. All right, so this is like not crazy hard, but okay. So in some sense, I'm recognizing A and B as a cover of P. So P has to be just a terminal. Yeah, so this completes the proof of the statement. So if I have any larger subobject that does include A and B disjointly, then I'm done. So now I have to find the C, right? If I want to complete my proof, I need the C. So where can I find my C? This is not going to work. Omega to the A is always zero truncated because omega is zero truncated because it's classifying subobjects. And so unless A is kind of like trivial, it's like zero truncated itself, in a general infinity category, this map is not going to be mono. And so here is kind of, I would say like up to here, most of the talk is kind of canonical in the sense that there's like kind of correct choices. And this part is, okay, like how I don't have any kind of like perfect reason how to pick this super object, this object that includes A and some disjoint point. But the idea that we did come up with, and so like when me and Jonas like were thinking about this, the idea we come up with is you can take A an object, and I have this true map into omega, and I can push this forward. And if I push it forward, I get this object A bar. And because I'm pushing forward along monomorphism, this is actually a pullback. So this is a mono. So there you go. This is mono like now in infinity sense. And now I need a disjoint point. What I can do is I can say I have a least subobject here sitting inside. I already have my least subobject. And I have a map, and this by adjunction corresponds to a map here. So I'm saying this is a pullback and this is false. So I have a map 1 into false going 1 into omega. And by adjunction, any map here at this level corresponds to a map on the pullback into A. And the pullback is just empty. So it's like the initial object. There's a unique map from the initial object to A, which corresponds to this unique map here. And now by pasting the map, this is in fact a pullback. So I should say, for fairness reason, this argument that I just said is actually not in the paper that is on the archive, but I learned about this argument like yesterday. So as a helpful comment. But I say like, oh, it's slightly simpler, but it has the same effect. So then the upshot of this is really you get A, you get A bar, you get 1, and here you have like the initial object as a pullback. There you go. So putting this together with the previous argument, then you can now do the same thing with B and multiply, and then you have your join of A and B sitting inside A bar times B bar. There you go. Cool. The argument is complete. So question, how about coequalizers? So we have initial object, we have coproduct, how about coequalizers? And the answer is coequalizers fail hard, right? So they just don't work, right? You can have local Cartesian closed infinity categories with subobject classifier that do not have coequalizers and push bars. And I give you two examples. One is you can take the full subcategory of eventually truncated spaces, and it's local Cartesian closed, subobject classifier, but the suspension of S1 would like to be S2, and S2 is not truncated at any level. It has, we don't know what the homotopy groups are, but we know there's infinitely many non-trivial. Another example is there's like this notion of truncated coherent spaces, which are like truncated spaces where all the homotopy groups are finite. And again, the same issue, right? So S0 is a truncated coherent space, but if you try to suspend it, then it wants to be S1, and S1 has homotopy groups Z, right, or Z. And that's, again, not finite. So coequalizers don't work, and there's no way to fix it. So the corrected conjecture then that we can prove, and to kind of complete the whole picture, is if you have a local Cartesian closed infinity category with subobject classifier, then you have an initial object and disjoint universal finite coproducts, but you do not generally have coequalizers. There's examples in both directions. And this leads us to the natural next conjecture. What do we need to add to our condition to do get coequalizers? The reasonable guess would be to add some kind of universes, right? So maybe if you have universes, you can kind of like use that in an efficient way. But I don't know yet. This is like more really like a conjecture that I hope to like tackle at some point. It's kind of like funny because it at least gives you a justification why universes are really necessary when you generalize from one Topos theory to infinity Topos theory. And with that, I thank you all for listening to the talk. And if you have questions, then I'm happy to answer them.
Great. Thank you very much, Nima. Let's thank Nima silently. Okay. Are there any questions?